we have basically in general 3D dynamics and 2D dynamics. Now in your ES204, what you probably mostly have seen and covered was 2D dynamics. Okay, so assuming that the motion is happening in a plane, let's say XY plane, so the rigid body has 3 degrees of freedom, right? 2 motions along translation along X and Y, and then a rotation about Z. In general, in space, it has 6 degrees of freedom, right? 3 translations, X, Y, Z, for which the governing equations of motion are second law of Newton. And then 3 governing equations for rotation, right? Where the governing equations for rotations can be basically seen here, right? Some moment X is some moment Y and moment Z. The moment vector is equal to the I matrix, and I's are here all what? They are moments of inertia times omega dot plus basically omega times I times omega, right? And these are our translations. So in general, we can say that in 3D, if I want to write it in a vector format for translation, we have sum of the forces is equal to mass times acceleration. So this is a vector equation. If you write it along any direction, X, Y, or Z, then you will get those 3 equations I just showed you. And then for rotation, you can say that the moment vector is equal to basically the I matrix times vector omega dot, and then plus omega cross I omega. Okay, right? Where here basically I is a 3×3 inertia matrix, and M is a 3×1, F is a 3×1, A and omega are 3×1. Okay, and this omega dot, you can also call it alpha if you want. So instead of omega dot, you can call it alpha, right? The angular acceleration. If you want, you can call it that. So these were the governing equations for translation and rotation. Now here you see that this small omega here is replaced by cap omega, and it depends on the frame with respect to which you describe basically omega to, or here the observing secondary frame, that's omega is the omega of that frame. So whether that is equal to the small omega or not. So it's a little bit more complicated, and then we call these set of equations, all of them, we call them Euler-Newton equations. Now these are 3D, as I said in that course. Probably you have not seen it. What looks more familiar to you is these guys that you have seen in 2D dynamics of ES204. So the motions along X and Y, and then rotation along the Z-axis, and here basically the second term is eliminated. If you see, only there is first term, and the reason for that is I omega and omega are parallel. Okay, so this cross product would go to 0. So under specific conditions, you can show in 2D case, I can say that omega and I omega are actually parallel to each other. Okay, so it's not always the case, but depends on your I matrix, but you can show that's the case here. Okay, because actually this is going to be a scalar equation. It's just a scalar because it's going to be only along z-axis when you have a 2D case. And so basically this omega is always along z-axis, and when you multiply a number by the z-axis, right? So let's say this omega is 2 times k and I is a number like 5. So this is going to be 2k, this is like going to be 10k. So when you do k cross k, that's 0. So this term goes away. You're only down to the first term, which you can see here. So we're going to use these equations actually in this course. And I'll talk about this later. If we need to, I'll talk about this later. These are just complementary material about like what happens in the moment equation if your reference point for moment and moment of inertia is not the centroid. Can you choose any other point than the centroid and write your moment equation? The answer is yes. If P is a point on the rigid body with arbitrary acceleration and it's not the center of mass, then I can write the moment equation about point P instead of centroid. It is going to be IP times alpha, and then you have some extra terms. So it's not going to be simply IP times alpha equals some moment about P. There is an extra term, okay, these guys here. So there will be some extra term again, and or this one. And I go through that in my dynamics course, but I don't want to convert this course into dynamics because that's a prereq. The other stuff that you probably remember from dynamics is if you want to relate the velocity of 2 points on the rigid body, this is how you do it. If you want to relate the acceleration of 2 points on the rigid body, that's how you do it. So these two important kinematics equations for 2 points on the rigid body. Then if you have 2 gears, pulleys, or chain and sprocket basically linked together, then we had something called speed ratio, which is the omega of the input over output, which you can show that is equal to the radius of output over radius of input. Also, you can show that that is equal to another term called mechanical advantage, which is torque out over torque in, which is also going to be the same as radius out over radius in. So we defined in dynamics, hopefully you have seen speed ratio and mechanical advantage. So basic mechanical elements were basically for translation, you had a damper, which I mentioned in this course. The force of a damper is a constant times the difference in the velocity of the two ends. The force of the spring is simply the constant of the spring times the displacement difference of the two sides, and then for a mass, force was mass times acceleration. You might say, what is this D that is shown here? Don't worry about it. D here is the derivative operator. So basically when it says dV means what? D, it's actually d over dt, not just differentiation. It's the derivative with respect to time. So dV means A. Okay, so in those notes, in that slide specifically, when it says d of something, d is equivalent to what? D over dt, time derivative. When it says 1 over d means the basically opposite of time derivative, which is what? Time integration, okay? Yeah, so when it says dv means what? Means d of v over dt, which is a. And when it says v over d, then it means integral of v dt, which is what? X, okay? So here 1 over v1 over d minus v2 over d means x1 minus x2, and here d of v means what? Means acceleration. So we know the spring, the damper, and the mass. We know the equations for that in translation. And then in rotary systems also we have a similar thing. So in rotary systems we have a rotary damper, And the torque of a rotary damper is constant times the difference in the omega, angular velocity of the two ends. For a torsional spring, the torque of a torsional spring is what? The constant of the spring minus theta 1 times theta 1 minus theta 2. And then the torque for it is what? Basically J times d omega. And d omega again means what? Means alpha, okay? So let me clarify this a little bit for you. Just because I don't want to skip it, I want to clarify everything for you before I start solving problems and going through problems. So here, this is quite obvious. It's V times V1 minus V2. It's a linear damper. Then we have here, this one, as I said, it means force is equal to K times x1 minus x2. This one means force is equal mass times acceleration. Then this one means, that's quite obvious, this one actually means torque is equal to K times theta 1 minus theta 2, and this one means torque is equal to J times alpha, right? D omega over d t. So that's the meaning of this d operator. By the way, I guess everybody knows what a linear spring and a linear damper is. As I mentioned in car suspension, the spring is this one, the linear spring, and then the shock absorber is a linear damper, right? So car suspension, coil, and shock absorber. Okay, so as you can see, any of these pictures can be quite clear, but as you can see, there is the cylinder in which there is fluid, and that will eat out the vibration and waste it. Okay, that's called shock. And then the spring is around it, which basically gives system a restoring force to go back. Okay, so this combination that you see in suspension is a coil, and then inside it is the shock absorber. So that's the meaning of those two elements in real world. Now, where is a rotational damper and where is a rotational spring, or we call it torsional spring? So torsional spring is what you probably have seen a lot in toys or anything that basically you twist it and then let it go and it moves, right? Mechanical springs. So you have seen them a lot in paper clips and so on. So for this guy, the amount of torque that you need to apply to it to twist it for an angle theta or delta theta is K times delta theta. Okay, so this is called a torsional spring. So just telling you what this guy is in real world. And torsional damper actually comes from friction of lubricant on the shafts. So when there is a lubricant, that lubricant is applying a negative torque on the shaft, and so damping out the energy that you inject into the system in terms of torque. Okay, so torsional damper. There are also some physical ones too, like these, where basically the shaft is directly inside. So it's not like you're just spraying the lubricant on the shaft. The shaft is inside a chamber, and inside the chamber, the object is moving inside the lubricant liquid, and that will basically eat out the and damp out the mechanical energy. Okay, right? So that can be a mechanic. Here is showing clutch. and other things too, but I will not want to go there. I guess this can be a good example of a rotary damper. But the effect of a lubricant on shaft is considered like rotary damper. So now I want to go through a couple of examples which forces us to go back into dynamics and draw FBDs, free body diagrams, and then apply Laplace transform, and then find transfer functions, and then we do inverted pendulum on the cart, and then find the state space representation of that. So in these two examples, we review some dynamic systems for both translation and rotation, and then we apply our new knowledge to find transfer function, and then what? State space representation of the systems. And these are example 3-4, and then what? 3-5 and 6. So I'm solving 3 examples from your textbook here in detail, right? So let's start with the first one. So this is our first system. A 2 degree of freedom vibration system where you have 2 masses. They are connected to each other and to the ground using a bunch of springs and a damper in between. The degrees of freedom for the objects is only along x direction. You call them x1 and x2, so 2 degrees of freedom. And there is an external force U that is applied only to mass m1. So the system has 2 outputs, x1 and x2, and 1 input, right? So this one is input, and these 2 are what? They are the outputs. And then it says what is x1 of s over u of s, and what is x2 of s over u of s. As you know, when I have more than one input, one output, so this is not a SISO system, this is actually, we call it an SIMO system. Okay, this is this kind of system. Single input, multiple output system. And for this, there is always a matrix of transfer functions. In this case, the matrix is a 2-by-1, x1 over u and x2 over u. So it says find them, right? So in order to do so, we need to draw the free body diagrams first, right? So let's get started with those. So first, we draw our FBDs. So that's one. This is another one. And let's write. So what do we have? So this is mass m1. So there is this force m1g. There is a normal force n1. There is the external force u. I don't know why, but my pen does not always cooperate. Then if the motion of here on the right side is x1, the motion on the left side of this spring, so if you look at this spring, if you focus on this spring, the right side of it moves with x1, the left side of it does not move. So the difference between the displacements is x1 minus what? 0, and since when this object moves with x1 to the right, the spring has to basically be stretched, so it will apply a backward force to the left. So the force of the spring is going to be what? Basically k1 times x1, right? Or x1 minus 0 if you want to call it. Now on the other hand, this k2, on the right side of it, it is moving with x2, the left side of it moving with x1. So the difference between x2 and x1 is the elongation of this spring, and then you multiply it by the constant to get what? To the force. Now which direction is it? It depends on whether x2 is bigger than x1 or x1 bigger than x2. But it does not really change the assumption that you make here is not going to change your governing equations. So here you make an assumption. Again, the assumption is not going to change anything. You assume that x2 is actually x1. Yeah, let's make it realistic. x1 is bigger than x2. Why? Because x1 is subjected to the external force first, then x2 through the spring and damper. So we assume that x1 is moving more than x2. Okay, and that also means that if we take a time derivative, x1 dot is bigger than what? x2 dot also. So we assume both of these. So if that's the case, x1 is pushing more than x2. So basically this spring is compressed, right? Because the right side is moving less than the left. So it is compressed more than being stretched. Therefore, since the spring is compressed, it's gonna push back, right? So this force is gonna be backward. So it's gonna be like this, and the magnitude of it is K2 times x1 minus x2. The same thing for dampers. Since the left side is moving faster than the right side, you are compressing the damper, so it's going to push back. And the force of it is B times x1 dot minus what? x2 dots. Okay, so this is the FBD of object 1. And something similar happens for object 2. So you have M2G, you have N2, then this K2 and B that applied these two forces to object 1, the reaction of them will be applied to object 2. So the same magnitude, just opposite direction, right? It's action and the reaction. And this K3 is pushed by X2, the other side of it is not pulled, so it is definitely will be compressed, so it is going to push back, and this is going to be K3 times X2, or X2 minus 0 actually, but we don't need to write it. So these are the two FBDs, and so now in addition to that, you also need what? A coordinate frame. So we use the traditional X, Y coordinate frame. And now we write down our equations of motion. We have one equation for X, one equation for Y, one equation for rotation. But first of all, these objects do not have any rotation, and they do not have any Y motion. So from those three equations that I showed you, from these three, the only equation that we're going to be writing is the X equation, okay? So if I write my equation for the X direction here, for object M1, what do I get? So I will get sum of forces in the X direction for this object is equal to and sum of the forces here is equal to U minus Kx1 minus K1 actually. K2 times x1 minus x2 minus b times x1 dot minus x2 dot. This whole thing is equal to mass of the object times acceleration of the object in the X direction. And for acceleration, I can write what? x1 double dot, right? Because the acceleration is second time derivative of the position. For FBD2, I have some force in the X direction is equal to positive K2 x1 minus x2, positive B times x1 dot minus x2 dot, and minus K3 times x2. This is equal to mass of the object times acceleration of the object in the x direction. So I have written my governing equations, right? And now, since we are looking into transfer functions, I need to take Laplace of these equations and assume what? Zero initial conditions. So I'm going to take a Laplace. So take Laplace, and then as I said, you need to assume what? Zero initial conditions, which means x1 of 0 is equal to x2 of 0 to be 0, and also x1 dot of 0 to be the same as x2 dot of 0, and then be 0. Okay, so these are my assumptions because I'm doing transfer functions. If you do so, here you will get u of s, and here I'm not going to say u of s, I just write it u. We know when I write it in capital letters, it is a Laplace transform. Okay, so it's going to be u of s, or if you want, let me write it to avoid confusion, minus. Now, I will basically take any x1 term to the right hand side, any x2 term will keep it on the left hand side. So if I keep the x2s on the left hand side, I have a negative k2 times negative x2, so positive k2 x2, and then I have a negative b times negative, so it's going to be bs x2 of s. Okay, so and on that side I have x1 of s times I have m1s squared. Then here I have negative k1 negative k2, and then I have negative b, which becomes positive b, so plus bs plus k1 plus k2. And then similarly, here on the bottom equation, I'll take my x2 terms to the right hand side, keep x1 terms on the left hand side, so I will get k2 plus bs times x1 of s to be x2 of s times m2s squared plus b times s plus k2 plus k3. Okay, so these are my governing equations in Laplace domain, and I will call them 1 and 2. Now, in order to find my transfer functions, remember when I want to find my transfer function x1 over u, okay, I'm just looking into the effect of u for x here, u in y. So what I need to do, I solve from these two equations, one time x1 over u, one time what? x2 over u. In other words, if I plug in 2 into 1 and eliminate x1, then 1 will be one equation between x2 and u from which I can find x2 over u. If when I plug in 2 into 1, I get rid of what? x2, then 1 is going to be one equation between what? x1 and u from which I can find x1 over u. In other words, this is just two equations and two unknowns. One unknown is x1, one unknown is what? x2, and the known is u. So from these two equations, I should be able to solve for both, which if you do, you will get your transfer functions. Okay, and this is what you will get. So here it's going to be m2 s squared plus bs plus K2 plus K3 divided by M1S squared plus PS plus K1 plus K2 times M2S squared plus PS plus K2 plus K3, and this whole thing minus ES plus K2 squared. Okay, so this is going to be basically the transfer function for x1 over u, and x2 over u is actually very similar. The denominator is exactly the same. The numerator is different. So let me copy that. Okay. And the numerator of that is just PS plus K2, which is basically this guy. Okay, so you get both fourth order systems because you see s squared is multiplied by s squared, so the denominators are both polynomials of order 4. So these are your transfer functions, and that's how we solve for this as single input multiple output system, finding the transfer functions. Okay, so that's example number 1. Example number 2, which is a little bit more complicated, is this system, inverted pendulum on the cart. This also has 2 degrees of freedom, but this time one of them is translation x, the other one is rotation theta. Okay, and you need to first find the governing equations in example 3.5, and then in example 3.6, you have to find the state space representation of the system in terms of what? Theta and x here, and to do so, the problem is asking you to consider your your rotation angles theta to be small. So let me add something here for you, that assume theta is small. What does that mean? Means the sine of theta, you consider it to be theta, and the cosine of theta to be 1. Okay, so let me actually add that for you. When I say this, small means how much roughly? It means less than 6 degrees. Okay, so it means sine of theta is the same as what? Is to be approximated by theta. And then what? Cosine of theta is to be approximated by 1. Okay, so this is when they say assume theta is small, that's the meaning. Good, so let's go ahead and get this going. So and the mass of the pendulum is small m, the mass of the cart is capital M, and the cart is rolling on the surface, so we are not gonna basically deal with friction in this case. We are not even interested in rotation motion of the tires. So what we need to do is first we draw the free body diagrams. So one of them is this box, and the other one is the pendulum. Let me draw the pendulum actually. So the pendulum is like this. So what forces are acting on them? Of course, cap M times G, a normal force N. Then we have the external force U. And then at pin P, we have two forces, right? So there is one horizontal force and one vertical force. I call them PY and PX, pin reactions. Okay, so this is the FBD of the cart. And then for the pendulum, you have, of course, at the centroid, M times G, and then the reaction to those pin forces, correct? So PY and PX. So these are your free body diagrams. And this system, if you look, it has one input, U, and then how many outputs? Two. One of them is X, the other one is what? Theta. So again, this system is single input, multiple output SIMO system. Okay, now here, this object has only translation, so the only equation we write for this is X equation, because it doesn't move in the Y and it doesn't rotate. But the pendulum does general motion. It moves, its centroid moves in the X direction, the centroid moves in the Y direction, and it also rotates. So first I call this centroid point, I give it a name, I call it point C. Also note that this angle here is theta, and I use traditional X, Y, and Z. So X to the right, Y to be upward, and Z to be what? Out of the plane toward U. Okay, so here we start. For the box, we write the equation. It is going to be U minus P of X, correct? So if we say sum fx, it is going to be U minus P sub X is equal to M times X doubled up. That's the only equation, as I said, we are interested in. We are not going to write Y equation because it just gives us a relation between N and Py, both of them unknown. We don't care about them. Now for pendulum, as I said, you need all three equations. So for the pendulum, you have to say sum fx is, so this is for a cart or box. This is for what? This is for pendulum. Sum fx is simply px, that is equal to mass of the object times acceleration of the centroid in the x direction. So it is x of point C double dot. Note that x of the centroid and x of the box are two different things, right? Then some forces in the y direction is equal to py minus mg. It is equal to mass of the object times acceleration in the y of the centroid. And then sum of the moments about centroid, counterclockwise positive, y positive because the z-axis is out of the plane. This is going to be basically, if you look here, px has a moment that is counterclockwise, py has clockwise. So px is positive, py is negative. The distance between px and the centroid, this guy here, the whole length of the pendulum is 2L. So this is 1L, this is 1L, and this angle is theta. So this distance is basically L cosine of theta, and then the distance between py and the centroid is what? L times sine theta. So it is going to be positive px L cosine theta minus py times L sine theta, and mg does not produce any moment about the centroid because it passes through centroid. This is equal to I about the centroid times what? Times alpha, and alpha is what? Theta double dot. Okay, so these four are your equations of motion, and we have to get rid of some unknowns because all we need for the state space representation is the equations directly between input, which is u, and the outputs, right? So u is given, and the outputs are what? X and theta. So these other unknowns I mark by red, px, py, and then what? X of c and y of c. You have to get rid of them so that you find just two equations between ux and u and theta, okay, or a combination of both in the equations. Px, py, x of c, and y of c double dots have to go. How can I get rid of them? Well, I have two extra equations here because I have four equations, so that can take care of two of them. But x of c and y of c double dots, I cannot do anything about them unless I use kinematics, okay, because I have 6 unknowns in general and 4 equations, so I need 2 more equations, and that's all I get from kinetics. And as I always say in my dynamics courses, when your kinetics is dead end, go back to kinematics and try to find more equations from kinematics. How? Well, how can I write the x and y of the centroids in terms of x of the box and theta? Can I relate those two guys to the two other unknowns, x and theta? If I can, then 2 of them are gone. And that's not really hard to do, because if you look here, x of point P is the same as x, because this is a single object moving all points, is translation only. So you can say that x of all points is almost x of P, right? If you consider it like a particle, because for this object, rotation doesn't matter. You can treat the cart as a particle. So x of the centroid, if you called it x of centroid or P, which is right above the centroid, if x of P is x, then what is x of C? Well, if you see, it's this much, which we found that was called x, that was calculated to be L sine theta. That is, if you add that to x of P, that's going to be x of C. So clearly from kinematics, x of C is x of P plus what? L times sine theta, but x of P was x itself. What about y of C? Y of C is y of P plus what? L cosine theta, right? And you can say that y of P, depending on where you put the origin, but if you put the origin right at the same level as P, then y of P is what? 0, so this can go. So you get simple equations. X of C is x plus L sine theta, y is what? L cosine theta. And then from here, since you are interested in double dots, you can take what? You can take 2-time derivatives, right? Now, before I do that, I use those assumptions that I made. And the major assumption that I made was theta is small. So I said theta is small, therefore I said sine of theta is to be approximated by theta, and then cosine of theta to be approximated by 1. If I do so, then I can say x of C is simply x plus L theta, and then y of c is simply L. Now I take two-time derivatives. And so it gives me that x double dot of c is x double dot plus L theta double dot, and y double dot of c is simply what? 0. Now I call these guys equations 5 and 6, and those equations I found earlier, I call them 1, 2, 3, and 4. So first, I'm going to plug in 5 into 2 and 6 into 3 to get rid of x double dot and y double dot of c. Okay, and also in equation 4, for cosine of cosine of theta, I replace it by what? By 1. And sine of theta, I replace it by what? Theta. Therefore, if I do all of that, so as I said, 5 into 2 and 6 into 3, and I rewrite all my new 4 equations, I will get that u minus px is mx double dot. Then px itself is m times x double dot plus L times theta double dot. Then py minus mg is equal to mass times 0, which is 0. And then px L minus py L times theta is equal to something times theta double dot. And what is that something? That's I of c. And if you know from your statics, the moment of inertia of a slender bar with length L and mass m about the center is 1 over 12 ml squared. But here the length is 2L, so this is going to be 1 over 12 m times 2L squared, which if you simplify it is going to be ml squared over 3. Okay, so this guy is ml squared over 3. Now my equations look a lot better, and I would call them 7, 8, 9, and 10. So please pay attention that I always number the equations in order to write in an organized manner. Now what? Now I try to get rid of px and py. That makes life very nice for me. So first, I basically plug in 8 into 7 to get rid of px. I also plug 8 into 10 to get rid of px. Then from 9, clearly you see py is the same as what? mg. So then I plug that result 9 into 10 as well. Okay, so if I plug in, as I said, 8 in 7 and 10, and then 9 in 10, I will get two nice organized equations where u minus m times x double dot plus L theta double dot is equal to mx double dot, and then ml times x double dot plus L theta double dot minus mgl theta is equal to ml squared over 3 theta double dot. Now from here you can solve for x double dot and theta double dot, because they are the two unknowns that you can consider and u to be like a known value. So if you do so, then you will get mx double dot is equal to u minus mg theta, and then ml theta double dot is equal to m plus m times g theta minus u. Okay, so again, if you solve from these equations for theta double dot and x double dot, that's what you get. And now these final equations are ready to be used for the state space representation. So as you can see, I have two equations and both of them are second order. Therefore, I need four state variables to write my state space equations. So I define a state vector z to be equal to x and x dot, because I have x double dot, and then also what? Theta and theta dot. Okay, again, I need four, two for x and x dot, two for theta and theta dot, because my equations are on x double dot and theta double dot, right? And now, if I take a time derivative from here, you see that z dot is going to be x dot, x double dot, theta dot, and theta double dot. And I can write this as x dot, I write it as 0 times x plus 1 times x dot plus 0 times theta plus 0 times theta dot. Okay? I'm writing it in terms of the four state variables. X double dot from this top equation, it is equal to negative mg theta over m, so there is no x in it, and plus there is no x dot in it. There is a theta term, which is negative mg over m times theta, and there is no theta dot in it. Right, so from here I could find x double dot. Right, and so there is one extra term here that I actually have to add, and that is plus what? U over m. I will separate it then later into a B matrix. Now theta dot is simply, there is no x in it, there is no x dot in it, there is no theta in it, there is one theta dot. And theta double dot, if you solve for it from here, your theta double dot is going to be m plus m times g theta over ml, and then minus u over ml. Right? So I write that down here. There is no x in it. There is no x dot in that equation. There is a theta term. There is no theta dot in it. And there is a u term in it. So this is z dot. Now I write this z dot as, I write this as a matrix A times z plus another matrix times u, the inputs, correct? So I call this A matrix, and I call this B matrix, right? Z dot equals A times Z plus B times u. And where do I get the coefficients of this, and what are the dimensions? Clearly you see, because z dot itself is a 4 by 1, and z is a 4 by 1, and u is a 1 by 1, so matrix A has to be 4 by 4, and B has to be a 4 by 1. Now what are the entries? They come from these rows. So you see there is no x, so this is going to be 0. There is 1 for x dot, no theta, and then no theta dot. So these 4 coefficients come from these 4 guys. Then second row, there is no x and no x dot. There is a term of theta, negative mg over m, so I just write it, that coefficient. And there is no theta dot, and there is 1 u over m. So what should I multiply by u? 1 over m. In the first equation there was no u, so I can write it as 0. So if you want, I can add something for you here and say this is plus 0 times u. And this is also plus 0 times u, okay? So I can use these coefficients here. This 0 also is this guy. Then again here, 0, 0, 0, 1. Then 0u. And here 0x, 0x dot. M plus m times g over L, no theta dot. And then negative 1 over m times L. So I got my A matrix and B matrix. Now your output equation says output y, which in this case is, as I said, we have 2 outputs, x and theta. This is equal to some matrix times z vector plus another matrix times u, where again this is a 2 by 1, this is a 4 by 1, this is a 1 by 1. Therefore, the dimensions of the C and D matrix, this is going to be a 2 by 4, this is going to be a 2 by 1. Okay, and again we call this matrix C and we call this matrix D. So x, if I want to write it in terms of the state variables, x, x dot, theta, and theta dot, and then the input u, x is simply what? 1 times x, nothing times x dot, nothing times theta, nothing times theta dot, and nothing times u. And then what? Theta is what? Theta is nothing times x, nothing times x dot, 1 times theta, nothing times theta dot, and nothing times u. So that's my C matrix. This is D.